Lewis structure. We've figured out its molecular geometry. We've also gone ahead and got the bond angles. We're asked two more questions. We're asked to give the expected hybrid orbitals on the central atom, and we're also asked about the overall molecular polarity. So let me just erase this over here. So if we want to know about hybridization, we also look to steric number. So to predict hybridization, use steric number. And so we have a steric number of 5, and a steric number of 5 tells us that the type of hybridization on arsenic is sp3d hybridization. We say that arsenic is sp3d hybridized. And that was really all you had to do in this case. Now, you could show the hybrid orbitals on arsenic. So arsenic in its unhybridized form, arsenic original orbitals, arsenic is in group 5a, so it has 5 valence electrons, 2 in the s orbital, and 1, 2, 3 in the p orbitals. Those are the 5 valence electrons of the unhybridized arsenic. But when arsenic undergoes sp3 hybridization, it mixes the orbitals s, all of the p's, and later on we grab one of the d's that come later on in the sequence. And so we end up with 1, 2, 3, 4, 5 brand new sp3d orbitals. Now, if we take those 5 valence electrons and place them in these new orbitals, we get 1, 2, 3, 4, 5. And since we have 5 unpaired electrons now, we can form 5 single bonds, which is exactly what we see in arsenic pentafluoride. 5 single bonds, and that's only possible because in its hybridized form, arsenic now has 5 unpaired electrons in those sp3d hybridized orbitals. If it didn't hybridize, arsenic could only have 3 bonds, 3 single bonds, but here it clearly has 5 single bonds. Now, in this question, really, you only had to answer this. It's sp3d hybridized. They weren't asking for anything more than this in the question. Now, the last part of this question asks about polarity. We want to know whether this molecule is polar or non-polar. Well, we know that the bonds in this molecule are polar. Every arsenic fluorine bond is polar. Fluorine is really electronegative. Arsenic is much less electronegative. We know that the bond electrons are being pulled towards the fluorine atoms in every one of these bonds. Now, let's take the out of plane axial positions, which I have in that sort of orangey brown color. I know that bond electrons are being pulled towards this fluorine, and in the opposite direction, bond electrons are pulled towards this fluorine. Now, they're going to be pulled in equal but opposite directions, So what's going to happen to the polarities of these two bonds? Are they going to cancel or not?
They'll cancel.
They'll definitely cancel. Now, what about those in-plane green bonds? Well, those in-plane green bonds are separated by 120 degrees apart. And bond electrons are being pulled here, and here, and here, all in the same plane, 120 degrees apart. If we were looking from above, all right, the arsenic atom would be in the middle, and those 3 green lines would look something like this. 1, 2, 3. Those would be the green lines to each of those fluorine atoms. Those are the in-plane equatorial positions. And so now the question is, do these bond polarities cancel? We already know the brown ones cancel out. Do these green ones cancel out?
Yes.
Yes, they do cancel out. And so since all of the bond polarities cancel out, browns with browns, greens with greens, will this molecule be polar or non-polar?
Non-polar.
You got it. So all bond polarities cancel. So our molecule is non-polar. Okay. So questions about this particular example before I move on?
So are all trigonal bipyramidals nonpolar?
Yes, they are, unless they have different outer atoms. So for example, if this atom here was a chlorine instead of a fluorine, then it wouldn't be nonpolar. Right? Because then these green lines wouldn't have the same polarity, and since the green lines don't have the same polarity, it wouldn't cancel out. All right, but yes, all right, as a rule, if all the outer atoms are identical in a trigonal bipyramidal structure, it will be nonpolar. Okay, questions, thumbs up, so I can know if I should move on. Really important to know if I can move on, especially on days where you have lots of questions for me. I'm going to keep searching out the questions. Okay, yay. So let's take a look at the next one on the list, which is number 34. Okay, let's just delete this. Here we go, clear. Draw. So let's take a look at number 34. 34 gives us a molecule known as urea, and the structure of the molecule is given. It's H, N, lone pair, H, carbon, double bond, oxygen, lone pair, bond, oops, bond, nitrogen, again, same on both sides, okay. And in this one, we want to know which hybrid orbitals are forming the various bonds in this molecule. So this question is very similar to the last question that I did on the lectures involving hybridization. So this really relates to localized electron part 2 lecture. So if you have not watched the part 2 lecture yet, you are going to struggle understanding this. So please watch the part 2 lecture, all right, before you kill me with a million questions. So the first question is, which atoms in this molecule are not going to be hybridized? Will all of them be hybridized, or will only some of them be hybridized?
Only some of them.
Okay, only some. So which are not hybridized?
Hydrogen.
In this molecule, it's only hydrogen. Okay, why is hydrogen not going to be hybridized?
An outer atom. Oh, go ahead.
I'm just going to run quickly. Hey guys, I'm working. I know, but I'm hearing some bad language out there. Nothing like teens swearing at their video games. Mom's getting an education. Okay, so tell me again. Let me hear about this hydrogen and why is it not hybridized?
They're outer atoms bonded with a single bond.
That's right. In any molecule, an outer atom, non-centrally located, another word for outer is peripheral. A peripheral or outer atom that is only bonded with a single bond will not be hybridized. Now, if hydrogen is not hybridized, let's remember that hydrogen has just one electron in an s orbital. It's group 1a, it's S1. And of course, an s orbital is a spherical orbital, and there's just one electron in that s orbital. It's really 1s1. And well, that electron by itself is an unpaired electron in an orbital. That is the orbital that will be used for orbital overlap for any bond involving hydrogen. So in this molecule, an s orbital from hydrogen is being overlapped with some other type of orbital from nitrogen, which we're going to have to figure out. And the same thing is true for this hydrogen. The s orbital on a hydrogen is overlapping with some orbital on the nitrogen. Over here, the s orbital is overlapping and the s orbital is overlapping. They're all going to be used to overlap with some orbital on the nitrogens now. So we know that the s orbital is being used by the hydrogens for bonding. Let's just clean that up a little bit and make it prettier. There we go. Well, not a lot prettier. So now that we know that hydrogen is not hybridized and it's using its 1s orbital, well, what orbitals are the other elements using to form the bonds? Well, let's take a look at each atom in turn. Let's start with the nitrogen here. Now, one thing I want you to notice is the nitrogen over here is identical to the nitrogen over here. They're mirror images. Both of these nitrogens have 3 single bonds and 1 lone pair. Now, the first thing we're going to look at on the nitrogen atoms is their steric number. What's the steric number on both of these nitrogens? Steric number.
4.
It's 4. How did you get 4 as the steric number on both of these hydrogens?
There's 1 lone pair and then 3 bonded pairs.
There you go. 1 lone pair, 3 bonds. 1, 2, 3 bonds, 1 lone pair. So we've got the steric number. Now let's also remember that the steric number tells us something about the hybridization in a molecule. And if the steric number is equal to 4, all right, that means the type of hybridization is what is it? sp3. sp3. How do I know that? Because there's a table that you have to memorize that correlates steric number to the type of hybridization. So both of these nitrogens are sp3 hybridized. Now, how many hybrid sp3 orbitals are formed for an atom? How many do you make? So we know that nitrogen is using sp3 orbitals, but how many sp3 orbitals are formed when that type of hybridization takes place? How many sp3 orbitals do we make? Well, here's a hint. What is getting mixed together to make sp3 orbitals?
4.
Which of the original orbitals get mixed together to make sp3 orbitals?
1s and 3p.
1s and 3p. So how many orbitals did we mix together?
4.
4. So how many sp3 orbitals do we make?
4.
4. So we have 4 new orbitals. 1, 2, 3, 4. And these are sp3 orbitals. So nitrogen doesn't have s valence orbitals. It doesn't have any p valence orbitals. It did when it was a free atom, but in this molecule, those orbitals don't exist. In this molecule, instead, nitrogen has these 4 brand new sp3 orbitals. Okay. Now, how many valence electrons does nitrogen have? How many valence electrons?
5.
5. It's in group 5A. It has 5 valence electrons. And if I take those 5 valence electrons and put them in nitrogen's 4 sp3 orbitals, and I have to obey Hund's rule, they go in like this. 1, 2, 3, 4, 5. So now what do we see? Well, I see 3 unpaired electrons. And we know that unpaired electrons in orbitals are what are being used to form single bonds. So every one of these single bonds involves these 3 electrons in these 3 orbitals. That means that the s orbital on hydrogen is overlapping with an sp3 orbital here. It's overlapping with an sp3 orbital here. Oh, and there's another sp3 orbital involved over here. Same thing is going on for the other nitrogen. There's an sp3 orbital overlapped here, an sp3 orbital overlapped here, and an sp3 orbital overlapped here. What about these electrons right here? Do these electrons participate in bond formation?
They're lone pairs.
Ah, those are the lone pairs we see on the nitrogens. So we also know that this lone pair is in an sp3 orbital, and that this lone pair here is in an sp3 orbital. Okay, so now we've taken care of the nitrogens. Let's take a look at the carbon. So here's carbon in the middle. So carbon is definitely going to be hybridized. Let's take a look at the type of hybridization we expect for carbon. So let's start with the steric number on carbon. What's its steric number?
3.
It's 3. It's got 2 single bonds and a double bond. A double bond counts once, doesn't count twice. And that means the steric number on carbon is equal to 3. And if we look at our handy dandy table, what kind of hybridization takes place when the steric number is equal to 3?
SP2.
You got it. That tells us that carbon is sp2 hybridized. Now, how many orbitals were mixed together to make those sp2 orbitals?
3.
3, an s orbital and 2 p orbitals. So if you mix 3, how many new orbitals do you have?
3.
3. So if we have sp2 hybridization, we have 3 brand new, sp2 orbitals. But let's remember that in an atom, there aren't 2 p orbitals. There are 3 p orbitals in the valence shell of an atom. And we only used 2 out of those 3 orbitals. And because of that, there's a leftover p orbital. There's a leftover p orbital. So to answer your question, Doran, there'll only be leftover p orbitals if we don't use all the p orbitals. If we don't use all the p orbitals, there's going to be leftovers. So to make the hybrid orbitals, we use 2 out of the 3. There's 1 p left over. And so this is the set of orbitals that we have here. Now, at this point, we're going to take a look at the number of valence electrons on carbon. And it's got 4 valence electrons. Putting those 4 valence electrons in, 1, 2, 3, 4. All right, I gotta let my dog out. Come on, you come in, you go out, you come in, you go out. Let's go. There we go. Okay, so we have 4 unpaired electrons so that carbon can form 4 bonds, 4 bonds. Now we have to be very careful with that p electron. That p electron doesn't form any old bond. The p electron can only be used to form what kind of bond?
Pi bond.
Okay, or in regular language, since you can't tell what's going on in here, all right, for this particular picture, all right, we would say that this is only used for what? I agree, pi bonds, but we want to be a little bit more attentive to this picture here.
Double bonds.
Ah, it's only used for double or sometimes triple bonds, but we don't have this, I guess. So this is only used for double bond formation. So if the unpaired p electron is used for the double bond, that means the other sp2 orbitals are used for everything else. And so we're going to have an sp2 orbital here, an sp2 orbital here, one of the sp2 orbitals here, and then that p orbital is for the double bond. So that means these bonds between carbon and nitrogen are formed by the overlap of sp2 and sp3 orbitals, sp2 and sp3 orbitals. Well, that takes us to the oxygen atom. And you know what? I'm going to give myself a little more room. I didn't really give myself enough space here. So here we go. give myself some room here. There we go, a little bit more room. So even though the oxygen is not a central atom and is technically an outer atom, it turns out that the oxygen atom is in fact hybridized. And that is because the oxygen atom has a double bond. So only outer atoms with single bonds are not hybridized. And that means oxygen is definitely hybridized. It has a double bond. So let's take a look, and as we did before, take a look at the steric number on the oxygen. And what is the steric number on the oxygen?
Three
It is 3. How did you get a steric number of 3?
from one bond pair and 2 lone pairs.
That's right. It's clearly got the 2 lone pairs, and it's got that double bond, which is a bond pair. So it's got a steric number of 3, which means oxygen has the same type of hybridization as carbon. It must also be sp2 hybridized, because the type of hybridization is determined just by the steric number. And we've already determined that if it's sp2, we make 3 sp2 orbitals. 1, 2, 3. sp2, sp2, sp2. But since we only use 2 out of the 3 p orbitals, there's a leftover p orbital. So we get the same set of orbitals, hybrid orbitals, and a leftover p orbital for both the carbon and the oxygen. But a big difference, of course, is oxygen has 6 valence electrons. We know the number of valence electrons from the group number. So if I put 6 valence electrons in, well, here we go. 1, 2, 3, 4, 5, 6. So what do we have here? Well, let's note that this and this are the lone pairs. So I now know that these electrons here and here are in sp2 orbitals, sp2 orbitals. Now, we know that oxygen is forming that double bond, and that means one of its sp2 orbitals with one unpaired electron right here is overlapping with the other sp2 orbital, and the unpaired p electron overlaps with the other unpaired p electron to give us that double bond. So in double and triple bonds, p's can only overlap with other p's. P's with p's in double and triple bonds. And so now we've gone through and figured out which orbitals are involved in all of these bonds, step by step. Okay, questions?
Where does the last P come from again?
It's left over. So remember, before these atoms hybridized, all right, before hybridizing, there's an s orbital and 1, 2, 3 p orbitals. So when the mixing took place, either for carbon or for hydrogen, the s mixes with 1, 2 p's. And that makes this sp orbital, this sp orbital, and this sp orbital. But this p orbital is left over, and that's the leftover p.
Thank you.
Okay. We didn't have a leftover p for nitrogen because nitrogen is sp3 hybridization, so all the p orbitals were used to make the hybrid orbitals, so no p's were left over. So that was number 34. So 35 is almost identical. So I think everyone should give 35 a whack on their own. Tell you what, I'll do one of those molecules. So they're so almost identical, though, to the other molecule. Let's do acetone. Acetone is a little bit different. The first one, biacetyl, is almost identical to this example. It's so similar that it's not going to even offer you much of a challenge. So let me just delete this, erase. Let's take a look at number 35, which And the one I'll focus on right now is this one, acetoin. And acetoin, I'm going to draw out the full structure here because it's not shown in completion. There's a carbon saying CH3, but really that means there's 1, 2, 3 hydrogens bonded to that carbon. And then up next we have a carbon, and it says CH, which means there's a hydrogen bonded to that carbon. And then off this carbon, there's also an OH, which is an O and an H. So I'm just drawing it out in full, followed by a C with a double bond to an O, followed by another carbon with 1, 2, 3 hydrogens. So I'm just drawing this out in completion so that we can clearly see all the bonds in this molecule. Except for hydrogen, all the atoms in this molecule obey the octet rule. Carbon and oxygen obey the octet rule. They are in period 2. They cannot have expanded octets. Hydrogen has its duet every time. So we're going to also put in lone pairs where they're needed to satisfy the octet on both of these oxygens need an octet. So all I've done is I've completed the Lewis structure for acetoin. So if we're going to go through and do this particular molecule, I should note that this OH is exactly the same as the OH that we did in the last molecule. So if you look at that O double bond carbon bond, the C double bond O bond, it's exactly the same. It's exactly the same. Really, the only things that are going to be a little bit different here are this oxygen here and any of the carbons. Let's take a look at the bonding for just this oxygen and this carbon. So let's take the carbon I just showed in blue. So that carbon has a steric number of what? Blue carbon.
4.
4.
4. It's got 1, 2, 3, 4 bonds, no lone pairs. It's got a steric number of 4. For steric number 4, what's the type of hybridization? Hybridization. SP3.
3.
SP3. So it's SP3 hybridized. And how many hybridized orbitals do we get? How many SP3 orbitals do we make?
4.
4. By the way, do you notice that the number of new orbitals equals the steric number? So 4. 1, 2, 3, 4. Are there any p orbitals left over?
No.
No, because we used all 3 p orbitals. How many valence electrons does carbon have?
4.
It has 4 valence electrons, and so here they are, 1, 2, 3, 4. And those 4 unpaired electrons can be used to form 4 single bonds. And so this single bond here involves an sp3 orbital. So does this one, so does this one, so does this one. By the way, that hydrogen is not hybridized, so that hydrogen has an s orbital, and that bond here is ssp3, ssp3. Now, let's contrast that to the green oxygen, So green oxygen, as opposed to pink oxygen, which is just like the oxygen I did in the other example. Green oxygen, let's start with hybridization. What's the steric number on green oxygen?
Three.
Careful,
Oh, 4.
it's 4. It's got 2 bonds, bond, bond, lone pair, lone pair. So 2 lone pairs, 2 bond pairs, steric number is 4, which means this oxygen, like blue carbon, is also sp3 hybridized. Which means it also has 1, 2, 3, 4 sp3 orbitals with no p orbitals left over. But oxygen has 6 valence electrons, putting them in 1, 2, 3, 4, 5, 6. Well, we only have 2 unpaired electrons. Those 2 unpaired electrons are used for the bonds. So we're going to have an sp3 orbital making this bond and an sp3 orbital making this bond. But we also have a lone pair and another lone pair, and that's these lone pairs. They are in sp3 orbitals. And of course, on the other side, we have that hydrogen atom with its unhybridized s orbital. So you can go through and do these examples. They're almost identical to the one that I did before. So if you understand that first one and we're able to follow along, these are almost no different, almost no different. Questions? Or shall I keep going? By the way, how many sigma bonds and how many pi bonds are in this molecule? I want to ask that question here.
There's 11 and
Number
2.
sigma and number pi bonds. Let's
There-
start with the easy one. How many pi bonds?
2.
Careful,
1.
0.
just one. There's one pi bond. All right, that pi bond is right here. That's the pi bond. It's the second bond in the double bond. But all the other bonds in this molecule are sigma. A single bond is always a sigma bond. So these are all sigma bonds, sigma, 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 sigma. In a double bond, one of the bonds in a double bond is sigma, the other is pi. In a triple bond, there's one sigma and 2 pi's. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 12 sigma bonds in this molecule. Okay. Having gone through these examples here, I'm going to encourage you guys to work on the other questions here, 37, 39, all very, very similar. Now, one of the things that they have not done in these structures is shown all the lone pairs. So other than hydrogen, every one of those atoms should have an octet. And if the octet is not shown in the structure, you need to add some lone pairs. So be very careful with those structures. You're going to need to complete them by adding lone pairs where lone pairs are needed to complete octets. And so as I look at number 37, the nitrogens and the oxygens are all going to need lone pairs. As I look at number 39, the same thing is true. The oxygens and the nitrogens will need you to add in the correct number of lone pairs so that they both have octets. Once you've done that and drawn the molecules in expanded form, all you're doing is exactly what I did over here to figure out which types of orbitals are being used to form each of the bonds in the molecule. But these are very repetitive problems. It's good for you to repeat them. I'm not sure it's really good for me to keep repeating them right now. I'd like to give you a chance to work on them on your own and really figure out where you're stuck. Is that okay? Is that an okay plan, seeing how similar all of these questions are? Number 40, also very similar. All very similar, all giving you the same type of practice again and again and again. So I think my time is going to be better spent working on some of the other questions that you were asked, because really it's just bigger molecules, but the same principle. Okay, good. So we're all on the same page as that. All right, you guys should be now working on numbers 37, 39, and 40 for your own practice. So I'm going to clear this. And I said, I'm going to go backwards. So let's take a look at the chapter 8 questions I was asked. So flipping backwards. So let's see, chapter 8, 89, 109, 113, and 119.
Professor, I just want to clarify that 89 is part of 109, and I just wanted the N204.
So 89 N204. Okay, sure. So
Yeah,
just part A N204.
Yeah, but it's like from 109. It's the molecular geometry of N204, basically.
Okay, so let's just take a look at that. So N204. So N204 is a bit of a tricky molecule because, as it turns out, the 2 nitrogens are central in this molecule. And the oxygens are then attached to each nitrogen. We're always looking for symmetry where possible. So this is actually the stick structure of N2O4. And I'm surprised they didn't actually give you some hints as to this structure. Now, once we actually have this structure here, okay, it actually does. In 89, it actually shows you that. All right. In 89, it tells you that you think of the structure as O2N, NO2, which is N bonded to N right here, N bonded to N, 2 oxygens on each nitrogen. So you actually did have that as a clue to its structure. Now, to finish the structure and to think about its shape, etc., let's just, fill it out with our electrons. So we have 2 nitrogens, that's 2 times 5 valence electrons, and 4 oxygen atoms, that's 4 times 6, or 24 valence electrons. We're working with 34 valence electrons in this Lewis structure. Now, I've drawn 1, 2, 3, 4, 5 bonds in the molecule. 5 bonds is 10 electrons. So 34 minus 10 electrons in all those bonds, we're now down to 24 valence electrons. So now let's start putting our valence electrons on the structure. We start from the outside, we work our way in. So we're going to start with the oxygens. Oxygen obeys the octet rule. Each of those oxygens needs 6 electrons. 1, 2, 4, 6, 2, 4, 6, 2, 4, 6, 2, 4, 6. 6 times 4, that's 24 on the oxygen atoms. So at this point, I've run out of valence electrons. Is this a good structure? Is this a good Lewis structure for N2O4?
No.
No, it's not. Why is it not a good Lewis structure for N2O4?
Because you haven't completed the octet for the 2 nitrogens.
That's right. This nitrogen is missing an octet, and this nitrogen is also missing an octet. So, all right, what do we have to do when we're missing an octet? All right, if we're short,
Double
if we come
bond.
up short, what's the rule? What was that?
Double bond.
That's right. We've got to move some electrons around. We can't manufacture new electrons. We can't have more than what we have. We have 34. That's all we got to work with. All right, we have to shuffle the electrons around. Which electrons get shuffled? Well, we can
Oxygen.
take a lone pair and move it into position as a bond pair. So I could take this lone pair, for example, and move it over here. I could also take this lone pair here and move it over here. So if I move those lone pairs, now those nitrogens will have an octet, and the oxygens will also still have octets. And so, oh dear, excuse me, we're going to get this structure here. Oxygen, double bond nitrogen, single bond nitrogen, double bond oxygen. And here are the electrons that are left on these 2 oxygens. And here's the other oxygen, here's the other oxygen. And by the way, the electrons that are moved, here, they are here right now. Those are the electrons that I moved. Okay. Now, if we look at the nitrogens in the middle, how many electrons do each of the nitrogens now have?
8.
They have 8. All right, the nitrogens now have 8. 1, 2, 3, 4 bonds, 4 bonds, 8 electrons. All right, by moving those electrons over, all right, we now have 8 valence electrons for the 2 nitrogens, and all of the oxygens also have 8 valence electrons. But wait, you say, all right, I solved the nitrogen problem by moving electrons from the oxygen to the left and the oxygen to the right. But I could also solve the problem by moving electrons from here and here. I could have also done this. And if I had done this instead of the purple move, I did the green move, well, I would get this. So here's my alternate Lewis structure here. And I'll just show it in green here. Here we go, green, green. So which Lewis structure is better? Well, neither is better, right? And if neither is better, what do we have?
Resonance structure.
We've got resonance, you got it. And so these structures are going to have the same formal charges. What we have is resonance. We have resonance. So what else was asked about this molecule? So this was 109, you said? I'm on the wrong page. 109. 109 says, oh, predict the molecular structure. Okay. And bond angles for each molecule or ion in exercise. Okay. So we've now got this resonance structure. I haven't actually drawn it in perspective, have I? So if the nitrogens are considered central, the nitrogens are considered central. What's the steric number on each nitrogen? What's the steric number?
3,
3.
3. And what's the steric number on this nitrogen?
3.
Yes, it's 3. They all, it doesn't matter which way you draw it. The steric number on the nitrogens is 3. Now, steric number of 3 tells us the electronic geometry. What's the electronic geometry for a steric number of 3? I'll make some room over here.
Trigonal planar.
It's trigonal planar. So if we were to show this molecule in perspective, it would be nitrogen. Oh, that's a horrible, horrible way to do it. Let's try again. All right, it would be nitrogen, bond. Oh, I'm really having trouble with my stylus. Let's try again. Ah, that's a little bit better. Bond. Bond, nitrogen, bond, bond. So note that I've shown it trigonal planar around each of those nitrogens. Now we've got oxygen, 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 oxygen. Now I could draw this twice with the double bonds in the different locations, or I could recognize that these 2 electrons here and these 2 electrons here are being split between these 2 sites. In other words, I could show that these electrons are being shared here and here. And these electrons and these electrons are shared between these 2 sites here and here. So really these nitrogen-oxygen bonds are more like 1.5 bonds. And that's because the double bond is being shared between 2 sites on each of the 2 nitrogens. So technically, I would draw this twice. You should really draw this twice, but this is sort of how we would think about the resonance hybrid. And all the bond angles in this molecule are 120 degrees apart. So all of these angles here are 120 degrees apart. All of the angles here also 120 degrees apart. Any questions about this molecule?
I have a question.
Mhm.
So in the 2 resonance structures that you showed, you did the 2 purple and the 2 green. Is it possible to have one resonance structure that has the left purple and like the bottom green? Would that be considered its own resonance?
No, because it doesn't matter, because the resonance is only taking place between the 2 oxygens on the same nitrogen.
Oh, I see.
Okay.
If they're all sharing the
So there's
they're all-
resonance here on this side, and there's resonance here on this side. And it doesn't matter which you show. It doesn't matter which you show.
Okay,
Yeah.
thank you.
Okay, so that was the NO2 question, all right, for 89 and 109. So let's take a look at 113. So 113 says predict the molecular structure for SeO3 and SeO2. Okay, let's take a look at that one. Let's do SeO3. So as always, we're going to start by adding up our valence electrons. Selenium is in group 6A, as are the 3 oxygens. And altogether, we're dealing with 24 valence electrons. So we're going to put the least electronegative element in the middle, and that's going to be selenium. And it doesn't matter where you put those oxygens right now, just put them anywhere. We'll work on the shape later. And now we're going to go through and do our bookkeeping. We have 3 bonds minus 6 electrons in the bonds. So we're down to 18 electrons. We're going to put 2, 4, 6, 2, 4, 6, 2, 4, 6. And that's 18 electrons taken away. We're down to 0. Is this a good Lewis structure?
No.
No, selenium does not have an octet. How do we give selenium an octet?
By forming a double bond with one of the oxygens.
Does it matter which oxygen?
Not
No.
really.
No. All right, so we could take electrons here to form the double bond. Or we could take electrons from here and form a double bond. Or we could take electrons from here and form a double bond. So there are 3 possible options to get lone pairs, all right, to create a double bond. So what are we going to have here? We're going to have 3 Lewis structures. So we're going to have one with the double bond here. We're going to have one with the double bond here. And we're going to have one with the double bond, whoops, over here. Okay. So we're going to have resonance here. We're going to have resonance here. Or are we going to have resonance here? Ooh. So this is a rather interesting structure. If selenium had to obey the octet rule, we would get these 3 resonance structures. But does selenium have to obey the octet rule? Can selenium have an expanded octet?
Yes.
Yes, it can. So if selenium was limited to the octet rule, this would be the structure of SeO3. We would get these 3 resonance structures. So this is only if selenium obeys the octet rule. This is what we would end up getting. All right, but what was that?
A quick question, sorry. So will this generally apply for elements that are able to like disobey the octet rule? They don't, resonance wouldn't, I guess.
Oh no, remember you
okay.
can only expand your octet to 2 or 4 extra electrons.
Right, okay.
So you know, after that you can't keep expanding an octet infinitely. So yes, you can have resonance structures even for molecules that have expanded octets. Yes.
Okay, thank you.
Yes. I think some xenon compounds can have stable resonance structures, and xenon certainly has an expanded octet. So let's note, but selenium can expand its octet. Let's take a look at these 3 Lewis structures that I drew here. And what I want us to do is I want us to calculate the formal charge on the selenium atom in the middle and each of the oxygen atoms. Go ahead and calculate the formal charges right now for me. I'm going to have you guys do that. Calculate the formal charges on all the oxygens and on the central selenium. And let's remember, selenium is in group 6A and so is oxygen. Now, if you calculate the formal charges, you're going to find out that the double bonded oxygen has a formal charge of 0 in all of these structures. The single bonded oxygens, however, all have formal charges of -1. Now, what about the central selenium atom? Well, if you work it out, the central selenium atom will have a formal charge of +2. Now, what would we really like all the formal charges to be? For the most stable structure, all the formal charges would be
Closer to
Zero.
0.
0, exactly. Now, if selenium obeys the octet rule, we could not get all zeros. All right, this would be it. We would be stuck. This would be our structure. But selenium doesn't obey the octet rule. So if selenium is allowed to expand its octet, maybe we could get all the atoms to have a 0 as an oxidation number. Now, the only ways those two oxygens can get formal charges of 0 is to do what to them? The oxygens that have -1 formal charges. If I want them to have a 0 formal charge, what do I have to do?
Make double bonds.
Make double bonds. So let's suppose we had this, which you might say, that's crazy. And you're right, it kind of does look crazy because we're really fixated on the octet rule. Now, in this structure here, all of the oxygens have 8 valence electrons because oxygen cannot break the octet rule. So each oxygen has 8 valence electrons. Now, what about the selenium atom in the middle? All right, by putting all double bonds here, how many valence electrons does the selenium have?
6.
Careful. How many total? It's got 6 bonds, but how many electrons?
12.
12. So it's got 12 valence electrons right now, which means it expanded its octet from 8 by adding 4. 8 plus 4. Are we allowed to expand an octet by 4 electrons? Is that okay? When atoms expand their octet, it's typically by how many more electrons?
2 or 4.
2 or 4. So 4 is okay. So that tells me this is quite okay. All right. An atom that can have an expanded octet can go up to 10 or 12 valence electrons without being critical. All right. It won't go to 14. It won't go to 16. It won't go to 18. All right. But certainly it could go to 10 or 12 valence electrons. Now, in this structure, let's work out the formal charges. Well, all of the double bonded oxygens now have 0 formal charge. What about the central selenium? What's its formal charge now?
0.
Also 0. And so this is actually the true structure of selenium trioxide. Dorian, you have a hand up?
Yeah, I have a question about when do you know to make it follow the octet or to make it with the formal charges to make them 0? Does it always need to specify?
You should always check formal charges, especially if an atom can have an expanded octet. So if you know an atom in a molecule could potentially have an expanded octet, start out by drawing it obeying the octet rule, check the formal charges, and then test to see if by expanding its octet, you can do a better job with the formal charges and get them closer to 0.
So you should always
So
try to
you can't know by looking at it. You have to test it out.
Okay.
So you have to go through the steps.
Okay, thank you, Professor.
Okay. So this is actually the correct Lewis structure here. And it's only because selenium can have an expanded octet that we actually see 3 double bonds instead of 3 resonance structures. Now, in this question here, we're asked not just about the Lewis structure, we're asked about the molecular shape. So the steric number is, of course, 3. This is going to be a trigonal planar structure with bond angles of 120 degrees. So it's really like this: selenium, oxygen, oxygen, oxygen is the structure shape. So now you've seen this, perhaps you can go ahead and try the other one on your own, SeO2, SeO2. And see what you end up with for SeO2. Questions? We good with this one? I'm going to have you guys try SeO2 on your own. So that'll take us to number 119. Let's see, 119. Oh dear. Which molecules in exercise 115 are polar and have net dipole moments? Was there any particular one that you wanted me to do? Because it's going to require us to do all of 115 if we're going to do 119. I mean, we can. I can draw those molecules really quickly.
I can look for the ones that were.
I'll tell you what, have you drawn the molecules? You can tell me what the molecules look like.
Yeah.
So number 115, we have the following molecules: XeCl2, we have ICl3, we have TeF4, and PCl5. And if we're going to determine if they're polar or non-polar, well, we have to go through all the steps. We have to draw their Lewis structures. We have to think about their shape. What is their shape in three-dimensional space? And only once we've done those two steps perfectly correctly can we then assess these molecules, all right, for being polar or non-polar. Now, I'm not going to go through all the steps to draw these molecules, but I know what they look like, so I'll just draw them for you. So XeCl2 is this structure here. It's Xe in the middle. It's got Cl. It's got another Cl. And it's got some lone pairs on the central atom. How many lone pairs are on the central atom? Anyone? Well, it turns out there are 3. And those 3 are in the equilateral positions here, here, and here. There's a lone pair here, a lone pair here, and another lone pair here. So those are the other 3 lone pairs. And let's just try and clean that up a little bit. Okay, so they're the 3 lone pairs. So that's XeCl2. And it's a linear structure. It's a linear structure, but it is predicated on a trigonal bipyramidal structure. For ICl3, I is in the middle. And we've got 3 chlorines, 1, 2, opposite to each other. A third is over here, 3. And then we're going to have 2 lone pairs right here and here. And if you've done this, you can correct me. Turns out that this molecule is T-shaped. Note that the iodine in this molecule and the xenon in the other molecule, they have the same steric number. In fact, all of these molecules have atoms in the middle with the same steric number. So this is a T-shaped molecule, okay? In the third example here, TeF4, well, we've got Te, we've got a fluorine going up, a fluorine going down. We're gonna have a fluorine over here coming out at us, and we're gonna have one going back into the board, and we're gonna have a lone pair right here. And what we end up with here is a seesaw molecule. And let's just put the lone pairs on the fluorines. And in the last one, well, this is just like the arsenic one. It's phosphorus, chlorine, 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 chlorine. And this is a trigonal bipyrimidal structure. Okay, so all of these have central atoms with a steric number 5. So they all have a steric number 5 central atom. They all have the same electronic geometry. The electronic geometry on all 4 species here is trigonal bipyrimidal. Trigonal bipyrimidal. And since they all have the same steric number, they also have the same hybridization. So let's remember that the bonds are 2 different types of bonds. We have axial out of plane bonds. This one and this one are the axial out of planes positions. Out of plane axial positions. And the other bonds are the in plane, sometimes called equatorial positions. These are 120 degrees apart. And well, this one here is essentially identical to one that we did before, which was ASF5. This is essentially the same thing. So in PCl5, is it polar or non-polar? This one over here. This is non-polar. All right, it's just like this one that I did before. So the bond polarity here cancels with the bond polarity here, and this one, and this one also cancel out. So this is non-polar. This is a non-polar molecule, and it has no permanent net dipole moment. It's got a 0 dipole moment. Okay. Are any of the other structures non-polar structures?
Linear.
Linear structure is also non-polar. Why? Because this bond polarity is canceled by this bond polarity. Equal poles in opposite direction, so the bond polarities cancel out. So both of these structures are non-polar. However, the other 2 structures are polar. They're polar because the bond polarities do not cancel out. So in the case of ICl3, this bond polarity cancels this bond polarity. They cancel out. But is there anything canceling out this bond polarity here? No, there's nothing in the opposite direction.